In today's session, we will be talking about line integrals defined in the complex plane. Okay, so we will be considering curves in the complex plane or in the z plane, and we will be considering a function f of z defined at least on the points on that particular curve. Okay, fine. Then we will see properties, very much like properties of definite integrals that we have seen in the functions of real variables. Okay, and then we will see two different methods today for evaluating those line integrals. Okay, the first one is treating them to be antiderivatives. Okay, but this requires the function to be analytic. And the second one, which is a more general method, is a path dependent evaluation. Okay, so all integrals that you can evaluate by the method 1, all of them can also be evaluated by the method 2, but in addition to those integrals, there are also some other integrals which cannot be evaluated by the first method because the function is not analytic, by the method 2. Now, once we define the line integrals, see the properties and the evaluation methods, then we are going to find or evaluate an extremely important integral, okay, whose answer involves both pi and I. Okay, specifically we will be evaluating the integral of the function 1 upon z. Okay, it is going to be an integral along a closed curve, and that closed curve is going to be the unit circle mod of z equal to 1. Okay, and it turns out that the value of this integral is 2 pi I. So we will evaluate it using the second method, and you can see here that the function 1 upon z is not defined at 0, and 0 happens to be a point in the interior of mod z equal to 1. Yes, so that's why you can't use the first method there. Alright, and after that we are going to see an inequality which is more commonly known as the ML inequality, to estimate the upper bound on the absolute value of the line integrals. Okay, because we know that we cannot compare one complex number with the other complex number, we can definitely compare the absolute values. Okay, now this inequality may come handy in checking whether your answer is correct. Okay, so we are going to start learning line integrals defined in the complex plane. We will start by understanding the notation. Okay, so the notation is this. We are given a curve, any curve in the complex plane, which we are going to call the curve C. Okay, and usually either C or the equation of the curve is mentioned here at the bottom of the integral sign. Okay, and then we are given a function f of z, which is a function of a single complex variable z, and we have the complex differential dz. Okay, so if z is x plus iy, dz is going to be dx plus I dy. Okay, this is okay, let me put it in this way. This particular differential thing is inspired from chain rule of partial differentiation. Okay, or in general the chain rule. Okay, fine. Now the curve C can either be represented, the curve C can either be represented in the equation in Z, or it can also be represented parametrically, meaning both x and y can be expressed as a function of some other parameter, which is usually a real parameter, t. Okay, for example, suppose our path of integration is the circle mod of z equal to 1. Okay, or mod z equal to 1. So this is the equation of the curve C involving z, but we can also parameterize this, meaning if z is x plus iy, we may introduce the parameter t and write it as cos of t plus I times sine of t. Okay, so by doing this, we have successfully expressed z as a function of t. Okay, now z is the complex number, okay, x plus iy, or complex variable, but the variable itself has now been defined in terms of a real variable or in terms of two functions of the real variable, okay, cos t and sin t, and we may also specify the limits on t. Okay, so this is known as parameterizing the unit circle. Okay, now we will make use of parameterization process whenever required in our integration problems. Okay, but the main takeaway point is the equation of the curve C can either be expressed in terms of z, or it can also be expressed in terms of the parameterized version. Okay, x as a function of t and y as maybe some other function of t. Alright, so this is as far as the curve is concerned, and we also assume that the curve C is smooth. Okay, now usually at this level we are not interested in the assumption that we will by default assume that the curve is smooth. Okay, but I'll just tell you what we actually mean by this. Okay, so we say that the curve is smooth when the curve is continuous and has non-zero derivative dz by dt. Alright, now with this we can now approach the process of constructing or defining the line integrals. Please note that at this level we are not commenting on the behavior of the function f of z. Okay, specifically we are not at this level interested in knowing whether the function f of z is analytic or not analytic, but we expect the curve to be defined at all points on our curve. Okay, that's the least that we can expect from the function. Okay, that's the only thing that we have assumed. So with this background, we can now start defining the line integral. Okay, okay, so now we will simultaneously discuss the theory and look at the diagrams. Okay, so the approach is going to be very similar to the line integrals in the xy plane. Okay, because the z plane itself is the xy plane. Okay, so suppose we are interested in that portion of the curve C, okay, which starts at z0 and ends at zn. Okay, so we would like to consider this particular portion of the curve C as our path of integration. Okay, now what we will do is we will partition this particular portion of the curve into n subcurves. Okay, and for this to be done, what we will do is we will first try to find the associated parameter values. Okay, so step 1 is going to be partitioning the curve into n subcurves such that the endpoints of any partition, let's say endpoints of the mth partition, are Zm and Zm minus 1. Okay, these are the endpoints of the mth partition or m subcurve, let me say. Okay, so this is the start point and this is the endpoint. Okay, which means we will consider z0 to be the point on the complex plane where the parameter value is t0. Okay, and we will consider the parameter value tn associated with the last point of the path, which is the point zn here. Okay, so we will now get n plus 1 pairs of t's and z's. Okay, z from z0 to zn n plus 1, and the parameter values from t0 to tn. Okay, note that parameter is real, okay, with least value being a and the greatest value being b. Okay, now what we are going to do is we are going to consider arbitrary points which lie on C. Okay, but we are going to consider 1 point each from every subinterval. So let's consider this point from the first subcurve or subinterval, point 2 from z in between z1 and z2 on the curve, point 3 between z2 and z3, so on till this point between zn minus 1 and zn. Okay, now these points are still complex numbers, so I'm going to use the Greek letter zeta for this. Okay, so zeta 1 is going to be any point on the first subcurve, but that point should be only one. Okay, it can either be z0 or z1 or any point between them. You should consider only 1 point and repeat this process n times. So we will get n different complex numbers, zeta 1, zeta 2 till zeta n. Okay, all right. Now once we do this, then we consider the sum, and this sum will resemble the sum that we have already seen in single integrals, well, along the straight line, or in general line integrals in R2. Okay, so what we will do is we will first take the product of two entities. Out of those two entities, the first entity is value of your function f at the chosen point zeta m, which belongs to the mth subinterval. Okay, we will evaluate the function at that point. So this may very well be a complex number, and we are going to multiply this by the difference between the endpoints of the interval. Okay, so we are subtracting zm minus 1 from zm, and we know that these two are complex numbers. Okay, and we will call it delta zm. Now if we are constructing, or if we are taking n subcurves, we expect to get n such terms, one associated with each subcurve. Yes. Okay, now we are going to add them up. Okay, so we will get the following sum. M will go from 1 to n, and let us call this sum as Sn. Okay, so if we just continuously repeat this process for, I would say, larger and larger number of subcurves, making sure that the difference between the consecutive complex numbers goes to 0. If the limit of the sequence exists, we call it to be the line integral, and what I said is the largest delta Tm, okay, tends to 0. Well, I mean, sorry, it should have been delta Zm, which is as good as the partition norm. Okay, this is as good as the norm. Okay, so mod of the largest delta Zm should tend to 0, which ensures that these points come closer and closer to each other, thereby increasing the number of subcurves. Okay, so In the limiting case, we have the line integral, or what we call a contour integral. Okay, so line integral in the complex plane. So if we take the limit of this, if it exists, as n tends to infinity, this is going to be the integral of f of z with respect to z along the curve C from the complex number z0 to the complex number Zn. Okay, now we actually hardly encounter such a situation. Okay, so that means we are not going to actually solve integral problems using the definition. Okay, but it is important to know the definition, and well, yes, we have just now understood this completely. Okay, I have explained you the approach. You may find the similarities between the line integral or definition of line integral in R2 and the line integral here. Okay, fine. So yeah, that's it. So if you have any doubts, you can ask me. Otherwise, I will go to the properties of line integrals. Okay, fine. So let's now go to the properties of line integrals. The first property is the linearity property. Okay, so let me explain what this means. Suppose we have two different functions, f of z and g of z. Okay, and we are interested in finding the value of the integral along some curve C of a into f of z plus b into g of z, where a and b are constants. This will be a times the integral of f plus b times the integral of g. Okay, linearity property. Property number 2 is the path partitioning property, and for this we will need this figure. Okay, so consider a curve C which starts at z0 and ends at z. Okay, and suppose we are interested in finding the integral of f of z along this curve C. So we may partition the curve, meaning let's call this point as z prime. Okay, so we may now integrate f of z from z0 to z prime along the curve C1 plus the integral of the same function f of z with respect to z along the curve C2 from z prime to z. Okay, this is the path partitioning property, and sense reversal property is also very much straightforward. Okay, so suppose you are integrating f of z dz along curve C from z0 to z. Okay, this will be equal to negative of the same integral along the same curve, but the direction of integration being reversed. Okay, so these are the three important properties of line integrals of functions, complex functions of a single complex variable in the complex plane. Okay, linearity, path partitioning, and sense reversal. So any doubt here? No doubt? Okay, so let's go to the next part now. Alright, so now I will tell you the two methods of evaluating the line integrals. The first method is the method involving anti-derivatives, meaning using the integration formulas, okay, which we have seen previously. So this requires a theorem to be known, and in this theorem we will recall what we mean by analytic function. Okay, so the theorem's statement is this: suppose we have a function f of z Okay, and this function f of z is analytic in a simply connected domain D. Okay, so well, now the words simply connected domain, these do have specific meanings, but for us any curve that we will be using for our integration is going to be a part of simply connected domain. Okay, so let f of z be analytic in a simply connected domain D, then there exists an analytic function f of z, uppercase f of z, such that the derivative of f of z with respect to z is our original function in D. Okay, which means if za and zb, okay, are any two points belonging to D, and if we have a path from za to zb in D, then we can actually use the antiderivative formula to find the value of the definite integral from za to zb, and this also implies the path independence of the integral. Meaning, no matter what path you take from za to zb, you will always get the same value of the definite integral, but the only requirement is that, well, there are two requirements. First, f of z should be analytic, and second, the domain that we are considering should be a simply connected domain. Okay, so let us see an example of an analytic function. Okay, we will integrate it by the rules of integration that we already know, and then we will evaluate the same integral by the second evaluation method, considering a path of integration. Okay, question 1, evaluate the integral of f with respect to z along a curve C, given that z is x plus iy, the usual definition of z, and f of z is z cube. Okay, so we know the function. Now let's go to the path C. Path C is the curve, or that part of the curve that we want, which begins at origin or the complex number 0 and ends at the point 1 1 or the point 1 plus I in the z plane along y equal to x squared. So out of infinitely many paths which join the origin and the point 1 plus I, we will be considering the parabolic path y equal to x squared. Okay, now the first job that we should do is we should ensure that the function that we have is analytic. Okay, now we have already seen that any polynomial function is always analytic, but let's just verify the satisfaction of the Cauchy-Riemann equations. Okay, and for that we will need u and v in terms of x and y. Okay, so put z as x plus iy in the definition and use the a plus b bracket cube formula. Okay, so it is going to be a cubed plus 3a squared b, so plus 3x squared iy, plus 3ab squared, so that b squared thing is going to be minus y squared, so minus 3y squared, and finally plus b cube or minus I y cube. Okay, so thereby we have got the real and the imaginary parts of z cube. Differentiate u partially with respect to x, 3x squared minus 3y squared. Differentiate v partially with respect to y, 3x squared minus 3y squared. So the first Cauchy-Riemann equation is satisfied. Go for the second one. Partial derivative of u with respect to y, 0 minus 3x into 2y or minus 6xy. This should be equal to negative of partial derivative of v with respect to x. Okay, now the derivative is 6xy, and if you change its sign, it is going to be minus 6xy. So the second Cauchy-Riemann equation is also satisfied, and these equations will be satisfied anywhere on the complex plane, hence on the curve C. Okay, so we have obtained the required result for the application of the theorem. Alright, so The last part is perhaps the simplest. Okay, so the function z is z cube, the function f is z cube, so its integral is going to be z to the power 4 upon 4. Put the limits. Okay, at 0 z to the power 4 is 0, so you are required to find the fourth power of 1 plus I. Your calculator is capable of finding it, so no need to expand a plus b raised to 4. Okay, so if you do it, 1 plus I raised to 4, it will turn out to be minus 4 divided by this 4, so the integral's value is negative 1. Okay, so this is the evaluation method 1 using antiderivatives, only applicable for analytic functions. Okay, let us now go to the second evaluation method, which considers the curve and which doesn't require the function to be analytic. Okay, so let's go to that one. Evaluation method 2 based on path. Okay, now this applies to any continuous function which need not necessarily be analytic, so including the function z bar. Alright, well, now you have to first answer the question whether z bar is continuous. Okay, I'm sure you can do that. So let's go to the theorem which tells us when can we apply the second method. Okay, so suppose we have a piecewise smooth path C. Okay, meaning it may have corners in between, but we only have finitely many corners. Okay, so a piecewise smooth curve C or path C, and see, when we have a piecewise smooth path C, we can make use of properties of the line integrals that we have discussed. Okay, the path partitioning property. Alright, so we are given a piecewise smooth curve C, we are given a parametric representation of C. If not given, we can easily find it out, meaning you have to express the real part of z and the imaginary part of z as functions of t. Okay, and usually it is going to be any of the standard curves. Okay, and the parameter t takes the values a and b, it takes any or all real values between a and b. Okay, and the third thing that is given to us is an integrand which is continuous on C. Okay, now what we have to do is the following. If we have these many things with us, the integral of f of z with respect to z, okay, along the curve C can now be obtained as follows. Okay, we have to change everything to t, meaning wherever you have z, okay, you have to replace z by f of t plus I times g of t. Okay, so that will transform the integrand. Step 2, you have to also find the replacement for dz. Okay, so that replacement is the derivative of z with respect to t times dt. Okay, now this is perhaps the easiest thing to be obtained, very much like the integration by substitution. Okay, so this is f prime t plus I into g prime t dt. Okay, all right, so once we get this, then everything consists of only t, including the limits. So you can apply all the rules of integration and evaluate the integral. Okay, so let's now go back to the same problem which we have already solved by the method 1. Okay, function is z cube, curve is a parabola from the point 0 to the point 1 plus I. Okay, yes, and the equation of the parabola is y equal to x squared. Now sometimes to confuse you, what they do is, in addition to the parabola y equal to x squared, they also set f of z to be z squared. But don't get confused. Okay, f of z equal to z squared has nothing to do with y equal to x squared. Okay, its graph may not even look like y equal to x squared, only perhaps for some part of the x-axis. Okay, so that's the thing. All right, so coming back to the question, we already know the answer. Okay, we already know it. It is -1. But now let us verify our result by applying the theorem to, is it a piecewise smooth path? Yes, because we have only one equation representing our curve C. Can we find a parametric representation of C? Of course we can. Okay, recall the parametric equations. Okay, so choose x to be t, y can be now treated as t squared. Okay, now we will find the limits on t, okay, which are a and b in the theorem. So go to the starting point, either plug x coordinate or y coordinate and get the lower limit on t. Either of them will give you the same value of t, that is 0. Okay, and because the endpoint is 1, 1, even the higher upper limit on t will also be 1. Okay, because both x and y are equal to 1, and use the definitions. Alright, so once we get the limits or the values of a and b, now it's time to find two things. Okay, replace f of z by t, or everything that contains t, and so dz. Okay, fine. Now what is dz? Dz is dx plus I dy. Yes, x is t, so dx must be dt. Keep I as it is. Y is t squared, so dy must be 2 times t times dt. Okay, now let's go to f of z, which is z cubed. Okay, now what is z? Z is x plus I y. Now this is where we take into consideration the equation of the path, okay, or the parametric equations. X is t. Yes. What is y? T squared. So x plus I y raised to 3 will now be t plus I t squared to the power 3. Okay, because it is z cube. Now take t common, okay, from these two terms, and hence it will then be 1 plus I times t, and the whole bracket raised to 3. Now apply a plus b bracket cube formula. Okay, for t, write t cube, a cube plus 3a squared b, okay, plus 3ab squared, so this will also be real because we are squaring I, plus b cube, which will be minus I t cube. Okay, so what you can now do is you can consider this as your integrand, okay, which you will see here, and don't forget to multiply it by 1 plus 2i, okay, and then write dt, because the replacement for dz is not just dt, but it is 1 plus I times 2t, or 2i times t dt. Okay, so this is dz. Okay, and the first part is f of z, and as usual we have already got the limits on t, which are 0 and 1. So this is a and this is b. Now because t is a real number, we can now apply the rules of integration and solve it. The only thing that we should now worry about is I is present in both these terms, so it's better to first get it multiplied. Okay, yes, so keep t cube as it is outside the bracket, multiply the first bracket by 1 plus 2it. Okay, so let us multiply 1 minus 3t squared by 1, you will get 1 minus 3t squared. Now multiply 1 minus 3t squared by 2it. Okay, so this will result into, take I common, so it will be 2t minus 3t squared into 2t, so it is 6t cube. Yes. Okay, now do the same thing for I into 3t minus t cube. Okay, so again take I common, 3t minus t cube will be there as it is, right? And now take the product of I into 3t minus t cube with 2it. So what will you get? I squared will be minus 1, right? And then it is going to be 6t squared minus 2t to the power 4. Yes. Okay, fine. And from this you can even find these definite integrals on calculator, but I have done it for you. Okay, first term is 1 multiplied by t cube, so its integral will be t to the power 4 upon 4. Because the lower limit is 0, just replace t by 1, so that is going to be 1 by 4 minus 3 times. Okay, this is t to the power 5 integral t to the power 6 upon 6 1 upon 6 plus I into first term is 2t to the power 4, so 2 into t to the power 5 upon 5, so 2 by 5. Again we have I, minus 6 will be there as it is, t cube into t cube is t to the power 6, and hence 1 upon 7. Go to the next term, I times 3 times t to the power 4, so 1 upon 5. Okay, the integrand. Then minus t to the power 6 into I, so minus I into 1 upon 7. Alright, and then the last two terms, out of which the first term is negative 6 t to the power 5, so negative 6 into 1 upon 6, and the last term is positive 2 times t to the power 7, so it is 2 times 1 upon 8. Collect the real part, the real terms, and collect the purely imaginary terms. The imaginary parts, let me use blue color now for them, is 2 by 5 minus 6 by 7 plus 3 by 5 minus 1 upon 7. Okay, plus 3 by 5 plus 2 by 5 will be 1, minus 6 by 7 minus 1 upon 7, so minus 1, so 1 minus 1 0, so this whole thing will be equal to 0. So at least the imaginary part has turned out to be 0. Let's now go to the real part. Let me use pink color for this. Okay, 1 upon 4 minus 1 upon 2 minus 1 and plus 1 upon 4. Okay, 1 upon 4 plus 1 upon 4 is 1 upon 2, which will lead to the cancellation of minus 1 upon 2, right? So eventually you get minus 1, and that is the same answer that we got by the previous method. Okay, so the integral of f of z from 0 to 1 plus I is, the conclusion is, it is independent of C. No matter what path you choose. So you may now choose the following paths, okay, and try for yourself. Path 1, y equal to x cube. Path 2, y equal to x. Path 3, y equal to root x. You should get the same answer, which is root of, which is negative 1. Okay, all things will lead to the same answer. This is only because the function is analytic and the curve satisfies the properties mentioned in the theorem. Okay, it is piecewise smooth. Alright, so we have seen the two methods of evaluating a line integral in the complex plane. Now let us prove the following. Okay, the integral along the closed curve mod of z equal to 1. Okay, so this is the unit circle of the function 1 upon z with respect to z is 2 pi I, provided c is traced anti-clockwise. Okay, so this is the figure. I have shown the 4 points of intersection of the circle with the coordinate axis 1, I, minus 1 and minus I, radius is 1. Okay, fine. So see, now we cannot evaluate this by the first method because 1 upon z has a point where it is not defined, and hence it is not analytic, and that point is inside the function mod of z equal to 1. Okay, so if it is inside, then we cannot really apply the first method, okay, which would have then given us the answer as log of z. Okay, the function when integrated. All right, so we can't use it, so we have to follow the second method. Okay, meaning we will now bring in the parametric equations of this circle, and we already know how to parameterize a circle. Okay, x is cos theta and y is sin theta, one of the standard parameterizations, with limits on theta being 0 to pi. Okay, now let us also use the exponential representation of the complex number z, which is r e to the power I theta. Because we are on the unit circle, all complex numbers here have moduli 1 or absolute value. Yes, so C is then the curve e to the power I theta. There is actually no need to write it as cos theta plus I sin theta, as we shall find out. Okay, fine. So now we need to take care of three things. First, let's go to the limits. Okay, because our function is to be integrated along a closed curve C, the start point and the end point should be the same. So let us choose the complex number 1 to be the starting point. Of the integration process. And this will also be the end point, and we are tracing it anti-clockwise. Okay, so what is the lower limit on theta? The coordinates of this point are 1 0, so obviously theta will be 0 there. Yes, and now observe that as we traverse the circle in anti-clockwise direction, the value of theta increases. Okay, now you may not think of theta as the angle, but you may think of theta as the parameter. Okay, so theta has to lie between A and B. Okay, or you may also write it as less than B because it is a closed curve. So then B must be 2 pi. Okay, because you are completing a full circle once. Okay, and A is equal to 0. So as far as limits are concerned, everything is clear. Theta is going from 0 to 2 pi. Now let us talk about the function, okay, f of z, which is 1 upon z. So it is going to be 1 upon e to the power I theta. Yes. Now what about dz? Okay, if z is e to the power I theta, is it possible to find dz? Yes, that's pretty obvious. Okay, if z is e to the power I theta, dz is going to be e to the power I theta times I d theta. Okay, simple chain rule. Okay, so you can see d theta, dz there. This is dz. Okay, now you can cancel e to the power I theta, which will give you the integrand as I. Take it outside. You have 1 whose integral is theta. With respect to theta, put the limits. The integral's value is 2 pi times I. Okay, now you can also get this integral by other methods, okay, including the Cauchy's integral formula, but we will talk about that in a later session.